All right, so welcome back. Today we're going to get into a lesson called Proving Trigonometric Identities. This is going to be part one of proving them. This ties into what we started in the last section. Last section was simplifying trig identities, and it was using these tools that we've been building, and we will continue to build some more that end up being helpful in showing that the left side of an equation that's given to us is equal to the right side. And so we start off with something that looks like this. Sine x times cos x over 1 plus cos x is equal to 1 minus cos x over tan x. Really what this kind of comes down to is the fact that this question is really all about, are they equal? And so that is what we are going to be trying to show. We're going to do this in two different ways. We will show it that it's true for a specific angle, and that's called a verification. And we're also going to do something that's much more mathematically powerful, and that's to show that it's true for every given angle, every value of x. This is a true statement. So you won't be asked to prove or to verify something that isn't true. You'll only be asked to show something that is true in this course. It starts off with saying determine non-permissible values. In radians, this is always a general solution, and so we're going to realize that anything that has spent any time in the denominator, so that 1 plus cos x is going to give us a non-permissible value. Also potentially anything that is tangent, cotangent, secant, or cosecant, anything that is defined to be a reciprocal or has a rational component to it, that's also going to give us non-permissible values. So let's start off with the fact that 1 plus cos x may not equal 0. If that's the case, then cos x cannot equal -1. And where does that happen? Where is cosine equal to -1? It is equal to -1, of course, at pi. So we would state, therefore, x cannot equal pi. Now that's just within one revolution, so we will also need our general solution to that. So let's just put that one on pause for a second, and let's find what else we've got going on. Because we have tan x, whether or not it's in the denominator, we have tan x, so which is sine x over cos x. Because it's defined to be sine x over cos x, therefore cos x cannot equal 0. Where does that happen? Cos x being 0 happens at pi halves and at 3 pi halves. So x cannot equal pi over 2, nor can it be 3 pi over 2. That's part of it. The other part of it is this. If sine x is 0, if sine is 0, that's going to make a tangent equal to 0, and then this denominator here is equal to 0. So we do have to consider that as well. In this case, because tangent's in the denominator, tangent can't be 0, nor can it be undefined. So therefore, sine x cannot equal 0. Where does that happen? Sine x is 0 here and here. So therefore we conclude x cannot equal 0 or pi. When we put all of that together as a general solution, this third one that we just did with sine x, that kind of covers the first one that said 1 plus cos x can't equal 0. Altogether, when we look at all four of those, our angle can't be any of these, nor can it be anything that's coterminal with those, and so therefore x cannot equal, and we're going to, instead of writing 0 plus n pi over 2, we don't need the 0 on here. This just ends up being n times pi over 2. In degrees, it would be n times 90 degrees, And then we need to state that n is an integer. So I'm running out of room there. Looks a little messy, but you get the point. So n times pi over 2 is the general solution for your restrictions. What can x not be? Okay. Graph the two sides of this equation over the domain of 0 to 2 pi. Explain if it could be an identity. All right, so what that means is this. What it means is this, is if we graph these on your calculator, and I would encourage you, pick up your graphing calculator. Let's try to graph the left side of this equation as y1. Let's try to graph the right side of the equation as y1. Depending on what graphing calculator you're using, this might be easier to display or not. If you graph one of them at a time and turn the other one off, or you change your line style on your graphing calculator so that it'll graph one and then you can see it graphing the second one. The idea is the graph is gonna kind of look like this. It'll look like this kind of repeating pattern of this going on. So you're gonna have something that looks like that. And it doesn't matter if you graph the left side or the right side, they both look the same. So as far as we can tell, the graphs look the same. So make sure you've tried that on your graphing calculator. Explain whether it could be an identity. So to answer that question, we would just say, yes, the graphs appear to be identical. Graphs appear to be identical. All right, so just by looking on your calculator and by graphing it, that won't always be easy to do. Some of these trigonometric graphs, depending on how complicated they are, they might be really difficult to graph to get the right window settings to see what you're looking at. You'll have steep parts that and asymptotes that, depending on which calculator you have, might display differently or might display might be easier to tell or harder to tell. So the graphing component is not necessarily always the best choice, but it's just going to help us get our head around what's going on with this. Part C says verify that this equation is correct when x is equal to pi fourths. So what this is getting at is, do we have some evidence that shows that these are equal to each other beyond just by looking at the graph? And we're going to start off with two tables. And we will use LS and RS for left side and right side of this table. This is one of the very few instances on your diploma exam where they accept a abbreviation of some sort. So just calling it LS and RS. Some places call it LHS for left-hand side and right-hand side RHS. Either way, we should always start off with what our left side is, and in this case, sine x cos x over 1 plus cos x. And then we're going to drop equal signs down the left side. Do not do things like we would algebraically move everything to one side or do the same thing to both sides of the equation. We can't change what the left side is, and the left side is just this. We're going to manipulate the left side and the right side independently. In this case, because it's a verification, we're just going to substitute pi quarters. So we've got sine pi quarters, cosine pi quarters over 1 plus cosine pi quarters. Might be useful for us to just sketch where pi quarters is, just so we can get our head around those values. Sine pi quarters is root 2 halves. Cosine pi quarters is also root 2 halves. And downstairs we have 1 plus root 2 halves. This numerator ends up being 2 over 4. we're dividing it by this denominator, this 1 plus root 2 over 2. In this step, I'm probably going to take that 1 and I'm going to convert it. So I've got a common denominator. I'm going to call it 2 over 2 plus root 2 over 2. This is 1/2 divided by 2 plus root 2 over 2. Now we can take the reciprocal. We can't do that before this step. When we're changing division to multiplication, this needs to be one rational expression before we take the reciprocal. This ends up being 1/2 times 2 over 2 plus root 2. Ends up being equal to 1 over 2 plus root 2. Now, in Math 30-1, the curriculum does not require that we rationalize denominators. That was something that we learned in 20-1, and often it's going to be good mathematical form to rationalize the denominators. Let's leave this for now. Let's now work with the right side, and if we want to rationalize them, if they're not looking like they're equal to each other, maybe let's come back to that and we can simplify another step. But our goal is to make them so that they look the same. Our right side is 1 minus cos x. Same thing over here. 1 minus cos x over tan x. We're just going to substitute. So this is equal to 1 minus cos pi quarters over tan pi quarters. This ends up being 1 minus root 2 halves over root 2 halves is just 1. Or sorry, tangent of pi quarters is just 1, sorry. And then we end up with, so if this is just 1 minus root 2 over 2, this is equal to 2 minus root 2 over 2. And these things look very different. They both look kind of simplified. They kind of look both done-ish, but they are not the same. So there's some more. Did we screw up somewhere? Maybe at this point we're starting to question ourselves, but we haven't. Let's just see what we could do further with this. Let's try to rationalize our denominator on this side. Remember that rationalizing the denominator happens when we have a binomial by using its conjugate. So 2 minus root 2, both up and down. And maybe as soon as we do this, maybe as soon as we write this, we're doing this because it's our conjugate of 2 plus root 2. We're doing it because it's that. Perhaps you've noticed that our numerator over on the right side is 2 minus root 2. So perhaps we're on the right step with this. We're on the right track. Our numerator ends up being 2. Come on, pen. 2 minus root 2. And then our denominator ends up being the idea behind using this conjugate to multiply. 2 times 2 is 4 for those first two terms. The outside and inside terms will subtract to 0. They'll just melt away. And this ends up being 4 minus 2 is downstairs. My last step ends up being equal to 2 minus root 2 all over 2, which is equal to my right side. At some point, so now we therefore conclude, therefore left side equals right side, and we're done. Last thing that I want to mention on this, in particular, more so for proof. Once we finish this, once we have proven something to be true, you know what? I'm going to get to this when we do a proof of this. Let's just back that comment up for a couple minutes. Okay, so proven trig identities. It's usually deeper of what we're doing. Verifying, we're just substituting a value in and evaluating it and getting a numerical representation of the left side and right side, and they better be the same. That's kind of the thing. What we're doing when we prove that two sides to this equation are equal to each other is something different. We are showing that they will always be equal for any value of, in this case, theta. And so this ends up being quite a powerful tool. This ends up being, in a lot of ways, the backbone of what mathematics is this idea to prove a conjecture or prove that a theorem is true. So let's start with something. This one ends up being kind of simple. Let's start with cosecant is equal to secant theta over tan theta. As always, we should look at non-permissible values and state what can't be true. Because of cosecant is 1 over sine theta. Secant is 1 over cos theta. And it's dividing by tangent, which is sine theta over cos theta. Anything that spends any time in the denominator can't equal 0. Also, because we're dividing by tangent, tangent can't be 0, which would mean sine theta can't be 0. But for both of these, what we have here and what we have here is that cos theta cannot equal 0. Sine theta cannot equal 0. Cos theta can't be 0 means those two values of pi halves and 3 pi halves, theta cannot equal pi halves or 3 pi halves. Sine theta can't be 0 is these 2 points, so theta can't be 0 or pi or any multiples of pi. So altogether, we have therefore all 4 of those points, which just means theta cannot equal 0 plus n times pi over 2. We don't have to write the 0. So theta can't equal n times pi over 2, where n is an integer. So those are restrictions. We're going to start off by verifying that this equation is true for theta at pi thirds. So our LS is cosecant theta. Cosecant. In this case, in this verification, it's cosecant pi thirds. It's 1 over sine pi thirds. And when we think of pi thirds is up here. So that sine value is root 3 over 2. We have the reciprocal of that. So it's 2 over root 3. Let's leave it there for a moment. Our right side is equal to secant theta over tan theta. Which is 1 over cos pi thirds divided by sine pi thirds over cos pi thirds, which is equal to 1 over a half is 1 over cos pi thirds. Cosine pi thirds is 1/2 times, just taking our reciprocal, cos pi thirds is 1/2 is now the numerator. Sine pi thirds is root 3 over 2. And all of this tidies up to be 2 over root 3, which is equal to the right side. Therefore, left side equals right side. Okay, nothing new there, just a verification. No big deal. All right, so, but this is where something special is going to happen here. This ends up being a proof. We're showing that this is always true, that cosecant theta is perhaps equal to secant theta or tan theta. So what we did in the last lesson is we were just simplifying these expressions. So we were maybe looking at something on this right side, secant theta over tan theta, and simplifying what it looks like. And hopefully we would get down to, well, cosecant theta. whether we work with one side or both sides, one of the strategies that we should use, let's start to make a list for strategies for proving. So strategies for proving that they're true. Number one, work with the more complicated looking side. Work with the more complicated looking side. So we have cosecant theta on the left. We have secant theta over tan theta. The right side looks a little bit more complicated. The idea is we're better equipped to look for how to simplify these things instead of making them look more complicated. Strategy number two is going to be keep your eye on the other side. What I mean by that is even though we're going to be working with secant theta over tan theta, keep in mind that what we're trying to make it look like, and we're trying to make it look like cosecant theta. And so sometimes having that in mind is going to help us. So those are two strategies for now. We're going to build some more in as we go along through this, but there's two of them. Secant theta over tan theta. Let's go ahead and start to work with this. Secant theta is 1 over cos theta. We're dividing it by sine theta over cos theta because that's tangent. This is equal to 1 over cos theta times cos theta over sine theta. And you can see where we're going with this. This divides out, and we end up with 1 over sine theta, which we know to be cosecant theta. So we are done, essentially, with this proof. So a couple of things. Strategy number 3 is express trig functions in terms of sine and cos. So often we're going to be taking secant and calling it 1 over cos. We're going to be taking tangent and calling it sine over cos. So that's going to be a strategy. It's not always the best strategy. Once we start developing more powerful tools, we want to use more powerful tools to build better things. And so in this case, this one's nice and simple. There's really not too much to it. You probably could have done it in 3 steps instead of 4, and that's not a big deal. Now, last thing that I want to say on this page before I move on to the next page is this. So there's our 3 strategies so far. The one thing I want to say is this. We need to make our conclusion. Therefore, left side is equal to right side. Now, in mathematics, when we finish off a proof, we use a couple of different symbols. In this case, I'm going to use the letters QED. Often, so mathematicians at the end of a proof will write QED. And this is Latin. It's Latin for a phrase called correct, demonstratum. Which is Latin for what has been asked has been shown. And so at the end of our proof, you show that your proof is done by writing QED. Another way that we often see this done is just drawing a blank square at the end of your proof. That will also, instead of QED, you could do that as well. All right. Number one. Verify each of the identities first, and then prove the following identities. Okay. So I'm going to verify this first one, and then maybe I'll leave the others. We're not going to do a verification, but we will prove each of these, and you should state restrictions for each of these when we do our proof. Okay, so if we say verify, and we can choose any value. Keep in mind that if these things are actually true, if this is an identity, then it would work for any value of x. So verify for, let's say, I don't know, let's say pi over 3 again. And my left side would be cos x tan x. My right side would be sine x. My left side would be cos pi thirds, tan pi thirds. And therefore, cosine of pi thirds is 1/2. Tangent of pi thirds is √3 over 1. This is √3 halves. Sine x is sine pi thirds on the right side is equal to √3 halves. Therefore, so equals left side, and therefore left side equals right side. That's what a verification would do. As a proof, left side is cos x tan x. Right side is just sine x. So let's start with the more complex looking side, which is the left. And this ends up being cos x. Super easy one. And sine x over cos x is tan. This is just equal to sine x. Therefore, this is equal to the right side. Therefore, ls equals rs qed, or blank square. We should state what our non-permissible values are. And our only non-permissible values, anything that shows up in the denominator, is just cos x can't equal 0. Tan can be 0 because it's not in the denominator, unlike before. And so therefore, x, cos x being 0 happens at pi halves and 3 pi halves. So x cannot be pi halves, that's n pi. All right. Number 2. What we're going to do here is we're going to add to our list of strategies. So a little bit of a clue about what would be our strategy here is if I tell you that Pythagorean identities often is going to be something that we should look for. So strategy number 4, your Pythagorean identities. What did we have for Pythagorean identities? When we looked at this the other day, we said that cos squared theta, sine squared theta is equal to 1. And then any other combinations of that. So therefore, cos squared theta is 1 minus sine squared theta. Sine squared theta equals 1 minus cos squared theta. And so we can use those things to replace stuff that we have going on. We can also remember that if I take all of this, and if I divide it all by cos squared theta, then this becomes our second Pythagorean identity, which is 1 plus tan squared theta is equal to 1 over cos squared theta, which is secant squared theta. And our other one ends up being, if I took this whole original one and divided by sine, gives me cotangent squared theta. That's 1 equals cosecant squared theta. So those are my 3 Pythagorean identities, and we're often going to be looking for pieces of these, whether it's just one piece like tan squared and then changing it into terms of secant squared and 1, or whether what we have in this case is we've got 1 minus sine squared. So that's strategy number 4. So if I dive into this question, my left side is equal to 1 over tan squared x. My right side is 1 minus sine squared x over 1 minus cos squared x. Which side should we work with? Well, both of them could use some tidying up, but the right side looks more complex. So let's kind of start chipping away at that. And as soon as we start, we see that 1 minus sine squared is coming from here, coming from this Pythagorean identity. 1 minus sine squared is just equal to cos squared x. 1 minus cos squared x in the denominator. If I subtract cos squared from both sides of this, this is equal to sine squared x. And just tidying this up, this is equal to cotangent squared x. That's pretty much as simplified as the right side gets. The left side, 1 over tan squared, easy, cotangent squared x. So strategy of keep an eye on what the other side is maybe relevant here. Is we knew that we were trying to make 1 over tan squared x, and so maybe perhaps that's going to drive some of your steps at times. So this right side is now equal to left side. Therefore, LS equals RS, QED. Should state some restrictions here. What can't happen as soon as we have tangent involved, or secant or cosecant or cotangent, we know we're going to have restrictions. As soon as we have stuff in the denominators, we're going to have restrictions. And so therefore, tan squared x is in your denominator. So because we have 1 over tan squared x, therefore that can't equal 0, so the sine can't equal 0. It also has to be defined, so cos squared has to equal 0. Sine squared x cannot equal 0. Cos squared x cannot equal 0. So therefore, that's going to be all 4 of these. All 4 of those. We also have, and we should point out that 1 minus cos squared theta cannot equal 0 from this denominator over here. That happens when cos squared theta, or x, is equal to positive 1, which is going to be the same as sine being 0. So we don't really need that part, but we should conclude, therefore, x, not theta. X cannot equal n times pi over 2. And so we've seen that a few times. N times pi over 2, where n is an integer. So x can't be any of those values. That will often be your restriction, either all 4 of those points, or sometimes if you have tangent in the numerator, then you just have cos can't be 0. Anyway, so let's look for that. Number 3. Certainly the more complicated looking side is the left side. 1 over 1 plus sine x plus 1 over 1 minus sine x. Right side is 2 over cos squared x. So I'm going to try to make my left side look like my right side. Strategy number 5. So trig proof, strategy number 5. Number 5, I'm going to write it down here. Number 5 is try to get a lowest common denominator. If we have two rational expressions that are adding or subtracting, try to mash them together by getting the lowest common denominator and expressing it as 1. We're also going to have strategy number 6 here. And we got 5 and 6 are kind of the same. And we are going to look for conjugates. The fact that we have 1 plus sine x, we can't do a lot with it. But if I multiply that by its conjugate, then what happens? So I've got 1 over 1 plus sine x. I can't do much with that, but if I multiply it by 1 minus sine x, then perhaps you can see that that is going to end up being 1 minus sine squared, which is something we can do with. So we're kind of doing both of these strategies together. I'm going to need some more room here. My second term is 1 over 1 minus sine x. And here also, let's get the common denominator, which just so happens to be multiplying by its conjugate, 1 plus sine x. So this looks like it's on its way to nasty, but it really cleans up pretty nice. This numerator is 1 minus sine x plus 1 plus sine x. Be careful, if this was subtraction, we'd have to be super careful that we would distribute that into that binomial, but it's not. It's plus. So we're good. All of this is being divided by 1 plus sine times 1 minus sine. The beautiful thing here is this is 1 minus sine squared. And this is going to tidy up right about now because upstairs we have 1 minus sine x plus 1 plus sine x. The sine x is 0 out, and the numerator is just 2. This denominator, 1 minus sine squared x, Pythagorean identity, that's just cos squared x. If we didn't see that that was going on, we'd maybe have a look over here at the right side and realize, okay, I've created 2 in my numerator. Now what do I need to do in my denominator to make it look like this? And we would clue into that, and that would point us out that, okay, that's just one of our Pythagorean identities. And so therefore, this now is equal to my right side. Therefore, left side equals right side. UED. The fact that cos x can't be 0 is we have the fact that x cannot equal pi over 2 pi. Wow, lots going on with this. So what strategies did we use? Well, we used a common denominator because we wanted to add those 2 expressions together. We also used conjugates to create a difference in squares and tidy it up because we knew we have a Pythagorean identity in play. And so all of those things are rolled together as stuff that we used and that we worked with here. Next one. This one doesn't look too bad. This just looks like sine x times cos x times tan x is equal to 1 minus cos squared x. I'm going to ask you to maybe you give it some thought. Push pause for a minute and then try it out. And then when you get there or when you get stuck, hit. Let's go. All right. So changing this question into terms of sine and cos, we have sine x, cos x, tangent is sine over x, sine over cos, sorry. The cos x divide out, and we're left just with sine squared x. We would normally now express, we would change this right side to sine squared x. We normally would simplify stuff. It wouldn't be wrong to change the left side into 1 minus cos squared. Either way, this ends up being equal to the left side. Therefore, Ooh, Q, so sometimes in lowercase. All good. What can't happen? Cos x can't equal 0. Or x cannot equal pi over 2. It's n pi, being integer. That is it for now. I believe, yep, that's it. So, part one of trig identities, it's kind of a big thing. And these take practice. It takes, you need to develop some foresight. And you start to develop a sense of where you're going with this. And you'll see some of the same patterns. But keep an eye out for those strategies. Maybe write those down and keep those handy to consider when you're doing these. All right, thanks for watching. Good luck.